Thanks.
Yeah.
Okay, shall we proceed?
This method is used for solving divide and conquer and the other strategies. Greedy method is also one of the approach for solving a problem, or a design which you can adopt for solving similar problem. The problems which fits into this one, you can solve all of them. Let us understand what this method says. What is this method about? This method is used for solving optimization problem. What are optimization problems? Problems which demands or which requires either minimum result or maximum result. So for this, let us know a few terms. I'll explain it through an example. Suppose there is a problem P, and that problem is, I want to travel from one location A to location B. I have to cover this journey, that is my problem. For any problem, I'm taking one example, it can be any problem, similar type. Now, for this problem, there may be more than one solutions. Let us say, I can travel this by walk, solution 1, or I can take a bike, solution 2, I can take a car, solution 3, I can go by train, solution 4, and I can go by flight, solution 5, and there may be more solutions. You can give me more solutions. So my problem is to travel from location A to location B, and there are many solutions. You go like this or take this, and go there. But there is a constraint in a problem. I say that I have to cover this journey within 12 hours. This is a condition, constraint. So suppose I cannot cover it if I go by walk or by car, and so I can cover it only if I go by train or flight. Now, for a problem, there are many solutions, but these solutions which are satisfying the condition given in the problem, then these type of solution becomes feasible solutions. That's the meaning of feasible solution. A solution which is satisfying the condition given in the problem is feasible solution, though for a given problem, there may be many solutions. This is feasible solution, satisfying the constraint. Commonly we use the term, is it feasible or not? Feasible in the sense what? Satisfying our constraints or not, limitations or not. Next, if I say that I want to cover this journey in minimum cost. Minimum cost. I want to spend as much as less possible, then this becomes a minimization problem. So now as the problem demands a result should be minimum, then it is a minimization problem, right? Then out of these two solutions, one of the solution may be taking minimum cost. Suppose by train if I go, this is minimum cost. Then this is called as optimal solution. A solution which is already feasible and also giving me minimum cost, that is best results, that is best for me, minimum is best for me, then that solution is called as optimal solution. And definitely for any problem, there can be only one optimal solution. There cannot be multiple optimal solutions. That means there can be only one minimum cost. Minimum can be only one. There can be more than one solution, there can be more than one feasible solution, but there will be definitely only one optimal solution. This problem requires minimum result. Some other problems may require maximum result. So if a problem requires either minimum or maximum results, then we call that type of problem as optimization problem. Optimization problem is one which requires either minimum result or maximum result. So let us briefly look at the terms once again. Feasible solution means a solution which is satisfying some constraint. Optimal solution means which is achieving the objective of a problem, satisfying the objective of a problem, that is either minimum result or maximum result. A problem which requires a minimum or maximum result is a optimization problem. So greedy method is used for solving optimization problems. These are the strategies used for solving optimization problems. These three methods are for solving optimization problem. The approach is different. And every problem, whichever requires optimal results, some may be suitable here, some may be suitable here. This strategy can apply on it, or this strategy can be applied, or for some problems, all three strategies can be applied on them. So we will learn all these strategies through problems one by one. Now we are going to cover this greedy method. So we will start with greedy method. We'll understand what greedy method says, what is the approach. So next I will tell you about greedy method. What is its approach? Here is the general method of greedy. I have written an algorithm. Now, see, greedy method says that a problem should be solved in stages. In each stage, we will consider one input from a given problem. And if that input is feasible, then we will include it in the solution. So by including all those feasible inputs, we will get an optimal solution. So in stages, we will each time will take up our input and we consider it. And if it is feasible, we will include it. And like this, if we follow this procedure, we will get the optimal solution. So here a general method is given. If a problem is given and that problem is having an input of some size and n is the size, and it is having some data, some values, input values. Now it will go through all those input values from 1 to n, and each time it will select something from A and call it as X. If that X is feasible, that is one input. One by one, it will pick up the input. And that input, if it is feasible, it will include in the solution.
Please feel free to interrupt in case if there are any doubts or anything. Okay.
If it is feasible, it is included in the solution. So this comes under if. This is the general method. Now I will explain you through example. The approach of greedy method is that suppose if you have to buy a best car in the sense in terms of features, you want a best car, optimal. Okay, the cost will be maximum definitely. So but you want optimal in the sense what in terms of features. Now how do you choose a best car? So one method is you should look at all the brands and all the models of cars available in the world, or at least in your city. Then you can say that I have checked all the cars, then I have selected the best car. This is one approach for solving a problem. The problem is to buy a car. This is one method. This will be very much time consuming. You have to check each and every brand and every model. See, the cost may not be a thing. Sometimes a nice car may be better than costlier car. So checking with the features and you are deciding that this is the best car. So, but actually what is the method we follow? We first of all sort out the brands and we say that we don't want in this, we want, let us say you are selecting a brand that is Toyota or Hyundai, right? Okay, you are saying that these are the best brands for you. And in these brands, then again, you will select the top models, right? So you are not looking at the lower models. So again, you have sort out. Then again, you say that in this top model, the latest release car or the well-known car, well-tested car, you are picking up that. And you are saying that this is the best one. Is it really the best one out of all the cars in the market? For you, it's the best one. So what is the approach you adopted? You have adopted a greedy approach. So you have your own method of selection, and based on that selection method, you got some result and you are saying that this is the best result. That's how it is greedy. And definitely when you do this, you will become the best car. So you don't have to waste time in checking all the cars available in the city, available in the market. So that's it. So without checking all of them, you say that you select few and say this is the best car. No doubt, that's the best car, but the approach you adopted is greedy. I'll give you one more example. Suppose you are running a company and you want to hire some people. So when you have given an ad, some 1,000 people came to you for the interview. Now you will conduct some type of test, like first you conduct written test, and then you have a technical test or group discussion. Like that, you will have various phases of test, and you will filter the people. And finally, you select one person and you say that this is the best person out of those 1,000. Is he really a best person? Yes, according to your procedures, it's the best person. What was your selection procedure? Based on the selection procedure, he is the best person. And yes, you have got the optimal solution. So the approach is greedy. Many students complain that I was better than him and he got selected. They think like that, but really the person who got selected is the best one, definitely. So the approach that you are adopting. Now, I'll tell you, if you're selecting one person out of 1,000, then for all you should give a chance for written test, for all you should give a chance for group discussion, for all you should give a chance for technical interview and HR interview, then pick up the best one. This will be very time consuming and costly process. We don't do that. We simply filter the people and select the best one. This approach is called as greedy approach. So we have our own methods of selection and we blindly follow those methods because those are the known methods. When you follow known methods of solving a problem and you quickly solve it, that approach is called as greedy. So I have given you enough idea about Hi.
Yeah, so there are two particular approaches or two particular types of knapsack. The one which we were talking about sorting or in terms of minimization maximizations, it's this one, the normal knapsack greedy method, and the another one which is 0-1 knapsack, which is often the dynamic programming way. So maybe let's cover this one and maybe we can switch to problems after this video.
So Sagar, one thing, when I was doing the dynamic programming topic, so I think, I don't know, so these are the two categories of problem of for the dynamic programming. One is 0-1 knapsack, and other one is I don't remember, the regular or fraction. So they come into the dynamic programming category, right? So like now I'm confused when we are relating it to the greedy method. Of course, they also help in getting the optimized solution. And now we are relating the same concept with the greedy algorithms. But objective is same, to get the minimal or maximum optimized solution, right?
Yes, yes.
So my question is, are those considered like, I don't know, they will be considered in the dynamic programming category or like greedy? I don't know. So that's a little confusing to me.
Which problems are you talking about?
I mean, these algorithms, you know, like knapsack algorithms, are they considered under the dynamic programming or the greedy algorithms?
They are basically greedy algorithms, but knapsack, like as I mentioned, there are two types of knapsack. One is fractional knapsack. In fractional knapsack, we tend to go with some sort of sorting, some sort of optimization, which is, as he mentioned in the previous video, that usually it's a known method or it's a simple method on which we try to optimize or maximize or minimize. In terms of 0-1, we consider various possibilities of reaching out to the solution, as mentioned in the previous video. And out of those various possibilities we are trying to consider, we will figure out one particular solution, which is the feasible solution or sort of maximum, optimum, or whatsoever with the condition sort of solution. And that is to be done by some recursive tree, some decision tree, or some sort of, let's say if we want to optimize that part, then we often memoize that, and that's why it is called as dynamic programming. So not to confuse general dynamic programming with greedy best ways. Just think about uh, optimization, and wherever you can have fractional values to be taken out of given values, go with normal knapsack greedy approach, which is fractional knapsack. And if it's explicitly mentioned in the problem that you can either pick the whole unit or whole element, or don't pick it at all, that's it. That is 0-1 knapsack. Choose or not to choose, go or no go. That's something which we need to consider, and that dynamic programming, or not specifically dynamic programming, but like creating a decision tree should help, like with various paths or various paths to achieve solutions, and then comparing them and returning the maximum out of them.
So,
So
Sagar,
for the
yeah, Aditya, Sagar. So, just to let me know if the understanding is correct or not. Say, I want to go from San Francisco to New York. Okay, and I have bunch of names of cities, like one is Vegas, then some Denver or something, or Texas, and then some city in Florida, and so I have bunch of cities. So I want to find the route from San Francisco to New York. In dynamic programming, what I'll do is I'll always try to check that whether I should go Vegas or not. So what I will do is I will try to find out all the different routes. Say I can go from San Francisco to Vegas, and from Vegas to say Texas, and from Texas to Miami, and Miami to New York. This is one route. And the other route is Francisco to Vegas, Vegas to some other city, Denver or something, Dallas, and then from there, New York. So what I'm doing here is I'm trying to find out all the routes first, and then there is a condition, right? Is it minimum or maximum with the existing one or something like that? And I kind of filter out that path. In Greedy, what I will check is what all other cities from San Francisco I can go directly connected. And in that, step by step, I will check that, okay, this city is nearby. So I will go there. And then from that city, I will check which city is the nearest. I'll go there. Is that the greedy, or at least that's the difference between complete dynamic programming, where I'm trying to find out all the permutation and combination. And in greedy, it's not all the permutation or combinations are being determined. It's step by step that how to proceed in the next step, or is that correct? Or
Yeah, I would say that's the perfect explanation of explaining or the difference between these two. So the second one is like we are choosing the optimized one at each step, each individual step, rather than in first approach where we were finding out all possible paths from source to destination, and then later afterwards comparing between which one is optimized. So in the first approach, it's about end results, but in second approach, it is about always choosing the most optimized subcomponent, or I would say every element or every candidate that is forming the path.
So Sagar, can we then classify, like you might know the Dijkstra problem, right? Where at every spot we choose what is the next optimal path, right? So can that be like a greedy?
Yeah, that is a variation. Yeah, I feel maybe right now I won't be able to talk about it much because I haven't revised it recently, but I would say, yeah, that if like the weighted graph, wherever there is a weighted graph, it should be 0-1 knapsack.
No, 0-1 knapsack is like when you find all the possible thing and you end up in finding the optimized solutions, right? Of
So yeah,
possible.
so I would say, yeah, so even in that there are two types. Yeah, as you said, there could be fractional part as well, where we are, as let's say, picking up Ritvik's example, from San Francisco, if we are looking towards which one is the next destination, which might cost us less or the least, and we are going that way, it is same as the Dijkstra's problem, Dijkstra's algorithm, where we have a weighted edges and we try to choose the one costing minimum and then figuring out the next one from there on. But the eventual solution might not be the least cost, least cost output. That depends basically. So it's the same thing that Ritvik just explained.
Dijkstra is almost like a greedy algorithm, we can say, where at every step we choose what is the next minimum.
Yeah, it is. Yes.
Okay. And do you also know like unbounded knapsack? Is it same? Is it different from fractional knapsack? The unbounded.
I would say right now we should not be thinking about branch and bound or unbounded or this thing, the pruning and all those things. Those are slightly complex and subtle thing. If we mix all three of them together, it will be too much of confusion and too much of thing to digest. I would say at this point of time, since we are focusing on arrays, let's just think about fractional knapsack and just the basic optimization for minimum or maximum result, instead of talking about all three and getting confused. I would say, yeah, that's something I would prefer, but yeah, I'm open for suggestions if otherwise.
No, you're right. That was my question. My question was like unbounded knapsack is different from fractional. That's what you're saying. You're saying unbound is the other category, and the fractional knapsack is different. That's what you're saying.
Yeah, actually, it's a third category, but I'm not,
okay.
To be true right now, I'm not sure about how much is it different or how to actually explain that part, because I'm not in touch about that.
So fractional is again kind of, you have the limited quantity, right? And you are taking out fraction of it and trying to find out optimize. Unbounded, you can have the same way or same value multiple times. That weight and value pair, right? That's what I remember, but it's been time for me also. So I can take the same weight multiple times, and if the value, so it's not just one apple or one banana. I can have multiple apples and multiple bananas. So there is no foundation there. I can have put the same thing multiple time in my bag and get the optimal value. In normal knapsack, is just I can take one time and then I cannot take the same thing again, right? So
yeah,
right.
So basically in the second approach, it's just about permutations, various permutations, and whichever generates the maximum value, we go with that. In third one, it is like multiple permutation as well as multiple combination of each of the permutation. Like multiple combination means each of the element could be multiple times or all sorts of permutation, as well as all sorts of combinations with that.
Yeah, I would like to add one point. Like for unbounded knapsack, you can consider the example of the rod cutting problem, wherein you cut the rods into pieces, and when you try to join it, you can still pick up the same rod, same piece, and create the entire maximum length of it. So one such example for unbounded could be rod cutting problem. You can have a look at it.
Yeah.
That explains like why it is unbounded, because you can take the same input again and again to derive your output. Whereas in 0-1 knapsack, you can either pick one, and next time when you decide like what I have to pick up, you will not pick up the same that you have picked up earlier, right? If you have picked up 5 kg as a weight, next time you won't pick up 5 kg, you will pick up the remaining weights that you have in a given array, because 5 is already processed. That's
right. That's perfect. And how about the fractional knapsack then? That's what I was confused.
So fractional knapsack is like
is that a third category?
No, that was the first one that we were discussing about. Like initially when we were maximizing, minimizing based on some condition. It should be. I feel that I think this video might be able to make it really clear. So in a short one sentence answer for fractional knapsack is, consider that we have these 7 options. Out of the 7 option, whichever one is generating maximum value for money or maximum profit for weight, we will choose that. How like whatever quantity we can choose at this point, we can try to pick all of it. Once after picking up the maximum profit for weight element out of it, we will see that what is the next second highest profit for weight we can choose. So that way, that is fractional. And once we reach to the capacity, we will just stop there and we won't pick further. But in that case, there could be a unit of object, or it could be a fractional object. So let's say let's say initially we picked up something like this, and this. So after picking this, we are supposed to pick something like this, but we only have 2 kgs of weight left. So instead of picking 15, we will just pick 6. So that is what we are making like fractional weight here. So once we pick the fractional thing, we can just stop, because we might have reached our capacity of weights. I think he has mentioned the same thing in this video itself. Yeah, as Rutvik mentioned, non-fractional could be take entire weight and valuation, and fractional could be only take the weight which has the maximum value, or adding maximum or optimal value to our result. Any other doubts? Aditya, does that make is it clear to you now?
Yeah, that was helpful. The only doubt which I had, like, are there like 3 categories of knapsack? One is 0, 1, one is fraction, and one is unbound. So that's what I was thinking. Are there 3 or it just 2?
You should be like, I feel that it should be 3 categories of greedy. Out of that, one is the normal fractional knapsack, another is 0, 1 knapsack, and third one is the bounded and bounded, or branching and bounds part. I think he just mentioned that in last video as well.
Yeah,
right?
yeah. That's
Same
right.
thing.
So 0, 1 is can be considered for dynamic programming. That's what you're saying.
Yes. So basically, it's a recursive path, where we consider all possible start source to destination path. And since we use memoization, that's the only significance of dynamic programming there. Or if we are going with tabulated approach, I'm not really a fan of tabulated approach though. But yeah, if tabulated approach is convenient to understand a particular problem, then yeah, that could be just using the memory and then finding the optimization. So there is one problem: buy and sell stock 3 and buy and sell stock 4, I guess. These these two problems are really great example of greedy with dynamic programming. But in that case, they go with bottom-up DB, basically tabulated approach, rather than going with the recursive approach. So recursive approach is slightly complicated in that. So there exactly we are able to understand the difference between applying greedy in recursive way or applying greedy in normal bottom-up approach. Okay, shall we proceed?
Knapsack problem. There's a well-known problem. First of all, we will know about the problem, then we will see how it can be solved, and then we'll also understand how greedy method is applicable here and is following greedy method. Let us understand this problem. See here, some objects are given. 1 to 7 objects are given. Every object is having some profit associated with it, and every object is having some weight. So objects are there, every object is having some profit and every object is having weight. Okay, weight we understand. What is this profit? See, there is a bag given here. That bag is called as knapsack. The bag capacity is 15. These are 7 objects. Bag capacity is 15. There is a bag whose capacity is 15, let us say kg. Okay, it can be kgs also, pound also, it can be anything. So I'm assuming it as kg. Now what we have to do is, we have to fill this bag with these objects. And we will carry this bag to a different place and we will sell away these objects. We get that profit. So that profit is the gain that you get by transferring these objects to some location. So for transferring, you have to carry them in this container or bag. So I can also call this knapsack as container. This is a bag or knapsack. I can also call it as container. So the problem is a container loading problem. So we find this type of problems in daily life. A lot of goods are transported daily from one place to another place. Now the problem is about filling of that container with the objects. When it becomes a problem, if you have the objects whose total weight is more than the capacity of the container or a bag, if you have less, all can fit in, then no problem at all. If you have the objects more in number, their weight is greater than the capacity of a bag, then it is a problem. So already we have some objects here. So I have to fill this bag with these objects such that the profit is maximized. Profit is maximized. So this is a optimization problem and it is a maximization problem. Maximization problem. Can we follow greedy method? Yes, we can follow greedy method on optimization problem if it is suitable. Next thing, what is the constraint here? The total objects included here in the bag, their total weight should be less than or equal to 15 kg. This is a constraint. So I can give various solutions. I can say that just put only one object and take it. It's not maximum. I'll say all cannot fit in. It's not feasible. So it cannot be optimal. So there can be many solutions. You can say take this, that and all and fill this one, but we want maximum result. That's it. For a problem, there can be many solutions, but those solutions which are giving, the solution which is giving maximum result is an optimal solution. Let us see how to solve this one. See, what I'm going to do is for these objects, I'm going to include them. So I will write down whether the object is going to be included or not included or how much it is included. I will write down here X values. So here I will be writing X1 or X2 or X3, right? X values I will be writing. So this X value can be either 0 to 1. This X can be from 0 to 1. So it means I can also take fractions. Yes. So now listen one thing very carefully. This knapsack problem is for those objects which are divisible. I have something of 5 kg means I need not take all 5 kg. I can just take 2 kg also, 1 kg also. So these objects can be divided. So what type of objects? If I take an example, these may be vegetables. 7 kg of potatoes, 5 kg of tomatoes, something. So instead of taking 5 kg, I can take 2 kg also. Means it can be divided. Yes. So this is not about those objects which are indivisible. Let us say 5 kg grinder, mixer, 7 kg washing machine. It cannot be divided. It cannot take half of that washing machine. So I have to take the full one. So here I can take the fraction of an object also. So that's how whatever I am including, that can be a fraction starting from 0 to 1. Now let us see how to include these objects in the bag. What should be my criteria, method for including them in the bag? You may be saying that this is giving highest profit. Take that one first. Yes, that is giving highest profit. Take that one first. But I can say that first fill the bag with the smaller things so that I can get more and more things in the bag and I can make more profit. More things you carry, more will be the profit. So I prefer take these objects first with 1 kg weight or smaller weights. So your idea is also good. Take the maximum profit one. And my idea is also good. Take the smaller weights one so that I can have more objects. But what is the right method? I should select the objects which is having highest profit by weight. Is 18 is the profit. So I say that 18 bucks is the profit. Then that profit is for 4 kg. It's not for 1 kg, it's for 4 kg. So per kg, how much? So that's it. We should select the objects who are having highest profit by weight. Per kg, whoever is highest, that I should take. So I should calculate this one. So I will calculate profit by weight for all these objects. So this is 5 and this is 1.3 and this will be 3. This is 1 and this is 6 and 18 by 4 is 4.5 and this is 3. Now I have these profits and weights of all those objects. Yes, this is the right selection procedure for the object. So the object should be selected based on their profit by weight. So the one who is having highest profit by weight, that I should put it in the bag first. All right. Now this is the greedy method. Let us see what the greedy method is doing. I was explaining you the problem so far. Then I said on what basis I should select this. Now we decided that we will select the object based on their profit by weight. This is our procedure. Now greedy method says that first you decide how you are going to select the input, then go on selecting the input one by one. So we already selected the method. We are going to select them by profit by weight. Now we will be going on including them one by one. So which object I should include first in the bag? The highest profit by weight, that is 5th object. So I will include this whole thing. So now this is 15 kg, right? So 15 minus how many kg this object is 1. So now remaining 14 kgs I have. So I have included that 5th object in the bag and I got the full profit 6. Now who's next? This one. I will select this one also, this whole, all 2 kgs I will take. So this is 14 minus 2 kgs. Now I have 12 kgs remaining in the bag. Now which is the next object? So this is the highest, and this is the next highest, this is the third highest. I will select this object also completely full. So full means all 4 kgs I will include. This is weight, 4 kgs I will include. So this is 12 minus 4 is 8 kg. 8 kg I have included, right? So 8 kgs are remaining. Now which is the next one? So I have 3, these are 2. I can pick up any one. So I will select this object. So this is how many kgs now? This is 5 kgs. Don't look at the weight. Don't look at the weight. I'm selecting this one. This is giving profit by weight. So this is 5 kg and I'll be getting 15 profits. So the profit is same only. For both of them, it is same. So I'll select this. So how many kgs are gone? 5 kgs. So 8 minus 5, I'm left with just 3 kgs in the bag. Now next is which one? This one. So I will take this whole thing. So how many kg? 1 kg. So 3 kgs are there minus 1. Now I'm left with 2 kg. Now which is the next one giving the profit? So this one. So I will include this. But this is how many kg? 3 kg. How much I have there? I have only 2 kgs remaining. So can I include all these 3 kgs there? No. I will be including only 2 kg there. So this is 2 minus 2. 0 it will become, but from this one I'm not taking the full object, I'm just taking 2 kg out of 3. So this is 2 by 3. So I'm taking the fraction of this object. You said already, I told you that these objects are divisible, so I'm taking 2 kgs out of that. And what about this? This is not included. So I have a solution for this problem, and this is the solution. This shows how I am going to include the objects, which objects I should include so that I get the maximum profit. Now I have to calculate the profit and find out how much it is. I have just written here the values from 0 to 1. Now I will see total how much profit I get, and I will also verify the weight that I am getting 15 kg only or not. Here I write these values. 1 with weight 1 into 2 plus 2 by 3 into this weight 3 plus 1 into 5 plus 0 into 7 plus 1 into 1 plus 1 into 4 kg plus 1 into 1 kg. If I take this is 2 plus this is 2 plus 5 plus 0 plus 1 plus 4 plus 1. So this is 9, 10, 14 plus 1, 15. So yes, the total weight is 15 only. See, these are the x values. This is 0 from 0 to 1. So that I am multiplying with weights. So what is this? Sum of the xi into weight I. And that is less than equal to 15. So I have found out the total weight. I was just subtracting. Now I'm just verifying. Now let me know the profit. So for profit also, what I'll do is 1 into 10. 1 into 10 plus 2 by 3 into 5. 2 by 3 into 5 plus 1 into 15 plus 0 into 7. I will avoid writing it. Then 1 into 6. 1 into 6 plus 1 into 18. 1 into 18 plus 1 into 3. 1 into 3. This is the profit. So this is nothing but summation of xi into pi. Every x value is multiplied with profit. So this is showing how much quantity I'm taking, x. Now what is this total equal to? This is 10 plus 2 into 1.3 plus 15 plus 6 plus 18 plus 3. So this is 54.6. So that's it. Our total profit is 54.6 and the total weight is 15. Once again, I'll show you something here. See, these objects are given. Then what is the constraint given in the problem? The constraint is what? sum of the weights of the objects included in the bag should be less than or equal to capacity of the bag. Yes, we have done it. See, total weight should be less than or equal to 15. And this is satisfied. This is the constraint given in the problem. So we have taken that solution which is satisfying the constraint. Yes, the solution is satisfying. So this is feasible. And objective is what? Objective is sum of the weights, profits of the objects that are included should be maximum. This is the objective of a problem. And we have achieved both. Now, quickly, I will explain you how we have followed the greedy method. Once again, I'm explaining you, see, the objects are given and the bag is given. We have to include these objects in the bag such that the profit is maximum, but the total weight should not exceed that one. So we have to select some objects such that we guarantee that we are getting maximum profit. So we have decided the criteria of selection. Have we tried this object? No. Without trying, how you can say that that is the best one? Because the method we followed is best one. The method we followed is best one, that we selected those objects whose profit by weight is higher, and definitely whoever per kg value is greater, that will give you the maximum profit. So that's all about knapsack problem. There is one more problem called 0-1 knapsack problem. That is different from this one. How it is different? Here, fraction of an object is allowed, but there, indivisible objects, fractions are not allowed. So this is container loading with vegetables or fruits like this, which are divisible things. Anything that is divisible. And 0-1 knapsack problem will be container loading with indivisible thing. Either you include that whole thing or you don't include it all. So you cannot take part of it. So that's all. So I'll be making there in greedy, and then I'll.
Yeah, is it clear, Aditya or others who were?
Yeah, this method is clear. This method is clear, right?
Okay. Okay.
Yeah,
Great.
he clearly says. I mean, he clearly explains why this is fractional, because things which are divisible, like food or something like that, right? That can be, that's why we use fractional. But if it's not divisible, like washing machine or whatever, then you use 0-1, whether you have to take it or you don't take it, right?
Yeah.
Yeah, and also looking at this approach, I would say if we just have a category of bounded and unbounded, this is subcategory of bounded, because we are not considering the same object multiple times. It's like it's all on the assumption that this is the final quantity which we have for that object, and we can take fraction out of it. And if we go with this approach, the maximum fraction which we can take, we will take at first time itself. Possibility that once we will consider all the fractions and take out all the fraction and then come back to same object again to take more fraction out of it is very low in this approach. It looks like whatever based on the maximum profit or optimal solution, what we can take, we will take at the first time only. And unlike unbounded, we cannot take multiple times, hence. So, that's just my understanding, but yeah, it looks like
even I think this is the right way to take a step towards developing the intuition, I feel. Yeah. So
you can say fractional knapsack is the bounded knapsack, right?
Yeah, why I'm saying that, because say here object 1 has a weight of 2, right? So he take what object 3 first for 5, or sorry, whatever object we are taking, we are not coming back to take one again more than 2. Like like in unbounded, I can keep taking object 1 multiple times.
Right.
But
I get your point. Yeah.
Here, in the first time itself, we will find out that what max we can take out of it. And it's very, so that assumption itself makes that I cannot take that object more than what is given to me. Or, like in
a real interview situation, these would come out as a constraint. Like, for example, we would know whether we can pick a specific item more than once or not. or whether we can do fractionals of a specific combination. Is that accurate to say, or do we?
So here the profit 5 is the max, right? Profit divided by weight. So that ratio 5 is max. What I'm saying is he's not taking the same object multiple times
That's correct.
to get the optimal solution. He just went one time, and that's where it looks like it's the constraint is. So at least looking at this problem, it looks like, or this solution or this approach, it looks like there is some constraint that how many times you can take that, or how much you can take out of it. So
Correct. Yeah. So it might come out like a constraint saying that the interviewer might tell you like you can't pick more than one time a specific item to fill the bag or something like that.
Yeah, definitely. We should clarify or ask.
Fractional, correct? So whether we can do fractions or do we have to go with 1 or 0?
Yeah.
Helps. Okay. Yeah, makes sense.
Yeah, sounds good. Maybe, yeah, shall we stop here or go with the problems? I feel that maybe digesting this and choosing some problem which is almost similar to this is a better way to go forward. And the one which we have selected for today, I feel that maybe we can skip that one, and next session, like tomorrow, we can go with some sort of sorting or optimization, sort of the fractional knapsack one. So that so in previous session, Vinay, we were discussing about the meeting room and trying to put it into perspective of greedy, right? So rather than having a tough time doing that, we can maybe choose some problem out of the further problems for tomorrow.
Yeah, let's put some obvious examples and maybe we can think about it later.
Yeah.
The other follow-up I had was these kind of problems. Is the dynamic programming a more natural way to solve these, or are there other approaches to solve these greedy problems?
As I mentioned previously, like in previous session as well, I would say according to my understanding, I would rather choose the pattern. I would rather learn it or identify the pattern behind the problem. So there are few patterns which will definitely give you a clear approach, which is fractional greedy, and find out or figuring out dynamic programming solution for that could be tricky. But there are few problems where it is easy to identify that, okay, fractional greedy won't help here. So it's definitely going to be 0-1 knapsack. So I feel that once you identify the pattern, it's not optional. It's which pattern the problem is based on. Does that helps you?
So let's say we classify these greedy problems into one specific category, like it's a fractional and maybe.
So most of the array problems are sort of fractional greedy. That's what I have seen on a rough note. But yeah, and most of the graphs related problem are usually dynamic programming, as Aditya mentioned, the Dijkstra's algorithm, right? So there could be other ones that could be mostly dynamic programming, and then there could be game sort of problems, which are again which might fall under 0-1 knapsack, or they could fall under branch and bounds, which is like again the next level of complexity in this thing. So I would say, since we are into flow of array, for arrays, we can concentrate on 0-1 fractional knapsack for time being, and it is easy to spot the pattern in terms of arrays problem, that it should be a greedy and it should not need any complex processing. Just some sort of value for money or profit for weight sort of thing should be enough, and then sorting it and choosing it in just one go O of n, O of n log n solution are enough for that. So these sort of problems could be fractional, which we can concentrate at this point of time, I feel.
Sagar, we were doing interval problems, right? Like how did we, I mean, I think I missed last one. How did we suddenly jump into greedy? Was there any alternate approach to one of the problem that?
So meeting room problem are sort of like they carry the intuition behind the greedy ones. So in meeting room, we are not actually doing any complex processing or anything, right? So we are just evaluating a condition of which one starts first. We are aligning all the meetings according to that, and we are trying to optimize it on that on overlaps. Or let's say in terms of meeting room, we are trying to minimize it in terms of overlaps. So if we are trying to minimize the overlaps, with the minimum overlap, we are getting the meeting room required.
Right.
So that's the way to look at the problem, I would say. So that's why meeting room merge interval are sort of greedy approach, not true greedy, I would say, not true fractional knapsack, but they are good starters in this direction.
Okay. So what are the problems which we think of solving with greedy methods? I mean, where are we going next? That's what.
Yeah. So to be true, insert interval and partition label. So I would say partition label is a better greedy problem. But so there was one or two problem that I came across. In case if maybe for by today tonight or maybe tomorrow morning, I can try to put that in the group. I had noted it down, but I'm not able to figure it out right now. I think it should be something like out of employee free time or non-overlapping intervals or some sort of wall penetration sort of thing, like penetrating minimum bricks to break the wall sort of problem. It's in the Facebook list of problems, and it's one of the top frequent problem as well. So that is another one which is good to develop the intuition, I would say. So we can have that as a starter problem to look at this, and then we can complete rest of the ones which is easy to frame and easy to describe then.
We're going to do these interval problems, right? And we're also scroll down. It said greedy, right?
Yes.
So we are also going to see how we can apply or how we can think on the greedy lines for solving these problems. I mean, maybe a few of them, right? That's what you think.
Yes.
Okay. So we shouldn't confuse with dynamic programming at this moment.
No. At this point, don't even think about dynamic programming.
Exactly. Because then it tails to another one, right? It's like a series of thoughts, right? So we should stop there. I mean, we should just focus on the interval problems and how greedy is relevant over here.
To be true, the pattern I was talking about, so this pattern is interval problems, honestly.
Right.
The merge interval or sort of problem, or meeting room problems where they are categorized. But since these patterns are relatable, that's why I thought of covering greedy algorithm with that. So I feel that we should be going with pattern rather than going with each and every algorithm. So if a particular pattern is taking into account some of the algorithm, we can just cover them just like greedy. And that's the case here with the meeting room or sort of these interval types problem. So if you see for meeting room, it is just sorting. For merge interval, it is just sorting. So why what exactly sorting is making us is to choose the overlaps or choose the minimum or maximum types of meeting that could be attended sort of thing, right? Once if you extend this into adding one more condition of optimization, then that's a true greedy. So that's a fractional knapsack that is there in the video.
I see. Okay. Yeah. So if you can just help us to point out the fractional greedy problems or any problems from this meeting interval category, then we can relate it better. And
And then one easy way to spot this out. So when once we solve meeting room, merge interval, then it is so if we see this is just about merge all overlaps. If we see this is about all meetings or sort of thing. But the next the next equal for that problem could be return the minimum number of intervals. So there come the word minimum, or there comes the optimization part. So that's why I was saying that these problems are sort of prerequisite to this one, is just to develop that thought. Otherwise these are not actually categorized as greedy.
Makes sense. I see your point. Yeah, how they have introduced the optimal requirement for getting the optimal, which can take us to the greedy approach, or think about that algorithm, right?
Yes.
I see. Yeah, so in your list, which problems are greedy in this intervals, if you go back?
I would say this overlapping, non-overlapping intervals. I'm not sure about partition level. Let me check with that. But it is into the meeting room sort of category.
Yeah.
I guess another one is this. If I'm not wrong, employee free time should be the greedy one.
So non-overlapping, overlapping, and employee free time. These are.
Yeah. Maybe we can let's pick up this problem for tomorrow.
There's another problem I heard for some other group of people. Best time to buy a stock could be another.
Yes, that's the perfect one for understanding the dynamic programming type of.
Oh, that's dynamic programming. Okay.
Yes, it's
which problem did you mention, Vinay?
Best time to buy a stock.
Oh yeah, that's very dynamic programming or state. Yeah.
Gotcha.
So it's third one, like I would say third sequel of that problem. Right. So buy and sell stock 3 is the one I feel.
Right.
But I would say interestingly, so there was an interesting discussion around one group that I was discussing this problem with. So it's most of the people, or it's easy to perceive it as a dynamic programming in terms of tabulated approach, this one. But when we think about a recursive approach, or if we are already in a flow of recursive approach, I would say in interview, recursive approach is lot easier to explain, lot easier to write code for, and lot easier to get it into our positive side of interview, or like try to like convert the interview with that sort of understanding of recursive approach. So it's actually sort of choosing and not choosing, and how are we breaking down the problem into our choices, that sort of thing. So I would say that is a good opportunity to look deeper into the DFS or backtracking approach, and then memoizing it to convert it into dynamic programming. So I would say maybe just have a caution. If you are good with recursive or dynamic programming or AFS, then definitely think about this problem in that way, and don't look at the tabulated solution at all until you develop that intuition in terms of dynamic in terms of recursive approach.
I think following the recursive will be easier, and then coming down to memoization rather than just doing the tabulation or top-down approach, I believe, right?
I think that's subjective. So in my case, the first approach I came up with, or the first approach that I was able to solve or understand completely, was a tabulated approach. But that didn't give me the feel. But when I solved it when I look at other solutions and got the hint that how can it be done recursive way, then I guess that was I would say that's a bit of work, but then it was more logical. So it depends. Like it might not be the first approach, or or it's tough to develop that intuition. But if we are able to develop that level of intuition to make it really simple, like to frame the recursive condition, then that's the best practice, I would say. That's the expertise level of recursion or top down DP. Okay, shall we stop here and maybe consider non-overlapping interval for next session to begin with?
Yeah. And this is related to the greedy version,
Yes.
which we saw. Okay.
Yes.
All right.
So merge interval is something which does not involve greedy, but this non-overlapping intervals involves greedy. So that's just a bit of difference.
Got it. Got it. Yeah, that's a very nice way to connect the new algorithm.
Yeah. So in a way, like I would rather not perceive it as greedy. I would rather perceive it as pattern. And as you mentioned, by connecting in interviews, it is easy to spot out, because often interviewers don't stop with the merge interval problem. They try to add complexity and then try to go ahead in terms of complexity, especially for senior interviews. So I think it's best to practice this way right here instead of having a surprises in the interviews.
Sure. Once everything is done, just if this today's session is over, so if there are any problem for NP hard or NP plus or something like that, just in case to cover some topic which we never touched, or yeah, I'll also check on LeetCode if there is any tagged or something like that. But yeah.
Yeah, I guess I did solve one problem which was based on state, and there was some sort of NP hard, NP hard solution, or NP hard sort of follow up to that. I will try to figure that, but that was just one problem I ever encountered. I will try to share that maybe.
Yeah, sure. Thanks, everyone. Sorry.
NP hard, I feel, is like it's a next level of complexity. It should take a lot of time to just understand it and then get into that flow.
Yeah, sometimes what happens is, for me, it's been a long time and not planning anything, but sometimes what, interview says that I'm not looking for I'm just looking for your approach or something like that.
Mm-hmm.
And, the problem sometimes does not we can categorize as one of the problem which we know. So, just some part that what exactly this approach is or something like that. Just to just to discuss such things if comes up in that way. So yeah.
Makes sense.
Sure. Thanks, everyone.
Yeah. Thank you, everyone.
Thank you all.
Thank you. Bye.